So without
So last session we have discussed about the encoder and various ways to code and what happens if you don't take care of all
yeah,
possible cases.
yeah.
So today we will little bit of encoder, then we will go to another discussion.
Okay, okay.
So that little bit of discussion is this that yeah, in case of priority encoder, we have, let's say, you have I3, I2, I1, I0. There
Yeah,
you have none of the line enabled, and then one line is enabled. Then we have here one, then X here,
yeah,
then X here, and then X here. And then we have output. So O2, O1. So for this we have 0, 0, and for this also 0, 0. For this we have 0, 1. For this we have 1, 0. And for this we have 1, 1.
yeah,
And then we have status signal. So this status signal is 0 here, and for here 1, 1, and 1, and also 1. Now,
yeah,
to code this behavior, we don't use in Verilog HDL that case. We have to use case X or case Z.
yeah,
What happens is case X will take care of X and Z both, but it takes only for Z. So in case you have, let's
yeah,
say here, one Z, then this usage of this is okay, fine. But what happens if one of the input is X? Then if you
yeah,
use this case Z, then that is not going to take care.
yeah,
So that's why what is recommended is to use this case X. So now what we do is even the coding style also we will little bit change here. So
yeah,
module, let's say this is the priority encoder 4 by 2. And instead of saying like this, I3, I2, I1, I0, then O2, O1,
yeah,
we can put here simply I, and we can put simply here O.
yes,
And then you have your status signal here. So now what happens is, earlier case we used to put here input, then I3, I2, I1, I0, all of this we use it to put. But now what we have to do is instead this, we have to put this one and what is the range that we have for this I. So
yeah,
now we can comment out this one. Comments are single for single line forward slash. So
yeah,
now for output, earlier we used to do like this O2, O1, but since this is the vector that we wanted to use, so we use output and the vector size is 2 bits. So this is
yeah,
O. And we have one output that is yes. So what happens here
good,
if you put yes, comma yes if you put, then
yeah,
this vector size is also applicable to the S.
yeah,
So here that's why to avoid such unintentional this 1 minute.
yeah,
So to avoid this unintentional vector here, either we have to follow putting like this first scalar, you put the scalar first and then
yeah,
go for the vector type.
okay,
Or else just separate them. You keep with one keyword vector and with other keyword the scalar.
mm-hmm. Okay.
So that is the care that you're supposed to be taking here. So what is recommended is put this way, like all vector with one keyword and with another keyword scalar.
Okay.
So two separate outputs you have to write instead going with one keyword output. So the problem with going with one keyword output here is you may end up having like this situation.
Okay.
You first you may put the vector and then comma and then putting the scalar. In that case,
Yeah.
this vector size automatically compiler will treat S as a vector.
Yeah.
So
Yeah.
to avoid this, what we have to do is with a single keyword, first vector things you keep, then later you keep your first scalar, then later you keep your vector type, or else separate them with two keywords like one
Right.
time output for vector, the other output is for scalar.
Yeah.
Then you come here for actually writing this logic here always at the rate x we use. And this we have only if one statement is there, then you don't require this begin and end.
Hmm.
If you're
Okay.
going to have multiple statements, then you require that begin and end.
Yeah.
So now here we are going to put the case x is required to be used,
Yeah.
and then here this case expression here.
Yeah.
So this case expression, we have here simply our I. So
Okay.
because
Yeah.
here we have stated it as a vector.
Yeah.
So now here we have to write the case values. So if you write the case values here, that is for tick B 0, 0, 0, 0, and then colon. Now, what is that we want here? We want something if multiple statements are there, then again, my begin and end is required. Begin. Our O,
Yeah.
now instead of O to O1, our O is to tick B 0, 0, 1 statement. The other statement is your status signal is 0. That is another statement. And then
Yeah.
you put the ends.
Right.
Now you come to the another case value here 0, 0, 0, 1. Then again you put the begin and then your O, then two take B 0, 0, and your yes 1 this time.
Yeah.
So then you go with another case here, that is case value 0, 0, and then 1x here. So then this begin and then O, then two tick B 0, 1, then terminate with a semicolon, then S is 1, then end. Then 4 tick B 0, 1 XX colon, then you put the begin, and then your O is 2 tick B 10, and your S is 1. And then you put the end here. And then 4 tick B 1 X X X. Then you have begin, and then your O is 2 tick B 1, and then your S is 1. And then you have to have the default case also, else this is going to produce
Yeah.
latch. So in the default, so other than this expected cases, if other thing is coming, then what is that we want to do? So we want to do like 0 this and yes is 0. And then you have the end case.
Yeah.
So now we have this begin also. So that's why we require here after end case, end is required. And then end module.
Yeah.
So that completes your Verilog, of this priority encoder.
Yeah.
So with
Yeah.
this, we complete this one. Test bench, you please develop. If you are facing any problems, then I will assist.
Okay. Okay.
Test bench part, I'm not going to cover because already the way earlier been covered, like that you have to, you should able to.
Yeah. 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 I think I
So
said so.
now today we talk about 4-bit adder.
Okay. Can you pause for 1 second
Huh,
the video?
recording.
Yeah, the recording.
4-bit adder, you have to design using 1-bit adder.
Okay.
So here, this we have this kind of 4 bits means like this.
Yeah.
So then you add first these bits. So here we basically don't have any carry in that is coming in here.
Yeah.
So carry in is 0 in this case. So half adder also we will do here.
Okay.
So you get the sum here and then the carry out from the this first stage. You can call it as the first stage, and you
Yeah.
can call it as a second stage, and this is your third stage, and this is your fourth stage. So
Yeah.
from this is zeroth stage. In zeroth stage, we don't have any carry in. So first stage it can be done even using half adder, and but the other
Yeah.
stages require full adder.
Right.
Why? Because from the first stage, if there is a carry generated, that carry
Right.
is added along with the bits.
Carry forward. Yeah.
So that way you get the sum one, and if carry generated, it will go to the third stage. Then you have to again take care of that carry. Then if any
Yeah.
carry generated from the third stage, it will go to the fourth stage. Then
Yeah.
here you get the sum and the actual carry out.
Right.
So to build that, we have something like top. This is the black box. Inside the black box, we keep here one full adder because we exclusively want to work with full adder alone. In that case, we
Right.
require to have the 4 full adders.
Right.
So this is how the 4 full adders are. Now here you have here bits are coming in or here you can again if you say this as your A and this is your B and if A is a vector size of 4-bit and B is also a vector size of 4-bit, then comes here is a of 0 then B of 0.
Yeah.
And since this stage not having any carry in, your carry in bit is 0 here actually.
Right. Yeah.
This will generate you the S0. So
Yeah.
this stage also will generate one C0.
Yeah.
And this stage is actually going to take your other bits A of 1 and B of 1.
Right. Yeah.
So this stage will produce you the S1 and carry out that you get here is C1. And this stage is going to take A of 2 and B of 2.
Yeah.
So now this stage will produce you the S2 and then it will produce even carry out. And
Right.
last stage will take the bits A of 3 and B of 3.
Right.
This
Yeah.
stage will produce the S3 and this is actual carry out of that 4-bit 4-bit full adder, parallel adder. You
Right.
can call it as a
Yeah.
parallel adder because
Yeah.
parallelly you are required to give all of these bits. So,
Okay. So all the datas are coming parallelly, A's
hmm,
and B's.
hmm.
Okay.
So all this data will come parallelly. So that's why this is also a parallel adder. So
So if the data is coming
uh,
parallelly, how will the full adder number two understand that the full adder number zero, or maybe this,
I will, I
if I
will,
see,
I will talk about
okay,
this. So this
Okay.
is also called as a ripple carry adder.
Okay.
So the reason is carry is ripple through all of these stages like this.
Okay.
So that's why it is a ripple carry adder.
Okay.
So in this architecture, the problem is you will not get this sum until you get
Yeah.
this C2. And you will
Yeah.
not get this S2 until you get this C1. And you will not
Yeah.
get this S1 until you get this CO. So
Yeah.
that is the critical path. The delay will be more. So we switch to there is another architecture of CLA, that is carry look ahead adder.
Yeah.
There are several such adder circuits are there. Not only this ripple carry adder and carry look ahead adder. There are several carry skip adder is there. Carry save
Okay.
adder is there,
Yeah.
and cogstone adder is there, and
Yeah.
several Brent adder is also there. So, but this is out of scope. But we are not into the architecture's
Okay.
understanding. So, what I am telling is, uh, we as a designer, we're supposed to explore all the possible cases.
Okay.
That depends on your application. So this ripple carry adder will take area point of view less area, but
Yeah.
delay point of view more delay.
More. Yeah.
Whereas carry look ahead adder area point of view more area, but delay
Yeah.
point of view it is less delay. So there is a trade-off. What we say is there is
Yeah.
a trade-off. So the this depends on when you are doing some kind of research there where you explore about the architectures.
Right.
So that is about the brief about that. But now to build this one, this kind of thing we call in Verilog HDL with structural modeling.
Yeah.
Structural modeling. This is termed as a structural modeling. So in this structural modeling, you don't write any logic. If you see, look at this black box, you are not writing any logic. You are only connecting by taking the lower modules in a way that are required to be connected.
Yeah. Yeah.
So the leaf, we call it as a, let's say, leaf module, lowest module. So this leaf module or lowest module, you can describe in any of the possible modeling style.
Okay.
You can gate level. One is, let's say you are invoking, you are instantiating, not invoking. We technically say instantiating. So if you are
Yeah.
instantiating one lower module, there is another lower module, there is another lower module, like that many. So one may be
Right.
gate level might have been described, one may be at the data flow, one may be at the behavioral level, one may be still, that itself might be at the structural level. So
Yeah.
all of this may be possible in the leaf cell or lowest module.
Yeah. Yeah.
So our job is only use this one, two, three, four, and connect them in a way the requirement is
Yeah. To get the
to get
full idea.
actually intended application.
Yeah.
So that is what we have to understand here. So you let's do that one now. So
Yeah.
you what you do is first you have to have the file of that fa.v file,
Yeah.
and then this fa.v file you are using the module name you are using in a fa 4-bit dot v.
We have to also have the half adder, right?
No, are we using here half adder?
Uh.
Are you seeing
mm,
here in the black box half adder?
Oh no, no, not
Uh,
this one, but the previous diagram.
No, no,
The
here I already told this
this not needed.
no, no, listen, understand the point here. I already
Mhm.
told that, just a minute, where is this? This one is, oh, this one. So if this one, I want these colors are there again. Okay. So now if you look at this
Yeah.
first stage is not having carry in, na?
Right. Right. Yeah.
If carry in is not there, then only two bits, that job can be done by the half adder.
Adder. Right.
But the point here is you have a IC called full adder.
Right.
You do not have a IC called a half adder with you.
Okay.
In that case, you only have to accomplish your intended application, which is a 4-bit adder, using the existing IC,
Yeah.
that is full adder.
Okay. Okay.
So how do
Yeah.
you do means you give two bits, those are required to be given, but the carry
Yeah.
in since is not there, that you tie it to the zero.
Right. Yeah.
That's what the
Okay.
point I was making here.
Yes. Yes. Yeah.
So this is we are thinking in a physical point of physical in a reality while you perform
In a
experiment
hardware point of view.
hardware point of view, there you
Yes.
have availability of a full adder IC only.
Right.
You do
Right.
not have the availability of half adder IC.
Yeah. Yeah. Got it.
So the in such cases, then we have to go with the one full adder means this third input is given to tied to the ground.
Yeah. Yeah.
This is not used, na?
Right. Okay.
So that's what I was making the point here.
One question: if
Huh.
I have one full ladder circuit IC, so with that circuit, I will be using the. I can implement this ripple carry adder, or do I need four full ladder circuits IC?
What do you see, understand from this block diagram?
This block diagram, I think four ICs of full ladder needed.
Yes, obviously four are required. Now, physically, you think a physical point of view.
Yeah, okay,
You
okay,
are, see, again, I will take here one, another. See, you are asked to do 4-bit addition,
right.
and you are provided with 1-bit full adder physically. Everything is physical.
Yeah, yeah,
So what you will do, you have taken one IC,
yeah,
which is a 1-bit full adder.
right.
To this, if you give your this 4 bits are there, if you are giving A of 0 and B of 0, at that moment
Right.
of time, you actually what you accomplish here by putting another to the ground here, that is grounded here. This is grounded.
Yeah,
So you obtain S of 0.
right.
Now, how do you? But you haven't been given only 1 bit, na?
Yes, yes,
You have been given with the 4 bits, na?
yes.
So to do this 4-bit addition, then this LSB bits you have taken here given.
Yeah,
What
yeah.
about the other bits?
We have to consider the yeah.
You
Got
you
it.
take you take one more IC, na? Which
Yes.
you have been given as many require. You take like that inside and given full adder 1-bit full adder IC.
Yeah, yeah,
Then
yeah.
you
True.
what you do, you make use of that given 1-bit full adder again here.
Yeah.
You know that this stage is going to generate the carry that you will give here, that carry,
Yes.
and you will give the other bits waiting here, na?
Right.
Then this is not going to complete your task. So another
Oh
IC
yeah.
you will take.
Won't.
And you give this stage is going to generate the carry. So these bits, waiting bits, you will provide here, na?
Right. Yeah. True.
Like that. So what is the outcome of this discussion? Then you require to use the four
Four.
full adders.
Right.
4 full adders.
Right.
So in Verilog, how we do that one is you write one file and that is fa.v, that is full adder.
Right.
So let's say you are not keeping this in one folder.
Yeah.
If you are keeping in one folder, then the usage I will tell. If you are not keeping
Yeah.
in a same folder, then the usage how to use in Verilog that I wanted to teach you today.
Okay. Okay. Got it.
Apart from this structural modeling concept.
Right.
So now you write here module, your full adder has got A, B, C in and some CO.
Yeah.
And you do the type declaration input A, comma, B, comma, C in.
Yeah.
And you do your output declaration that is some, comma, CO. And
Right.
you do your coding here in any of the possible modeling style.
Okay. Yeah.
So I will be using for the sake of demonstration this assign, that is the data flow modeling assign. My sum is A XOR B XOR C in.
Right.
And my carry here is CO is given as A ampersand B or A ampersand C in or B ampersand C in. That is the Boolean expression, straightforward Boolean
Yeah.
expression.
Yeah.
And since I have done with my description of the logic, then I use
Yeah.
AND module.
Okay.
Now
Yeah.
what I do, I am there in the same folder. This is in one folder, practically where you are working in system, one folder.
Yeah. Right.
So in that same folder, you are also creating one file called fa4bit.b.
Right. Right.
So now here, this is module fa4bit, and here you are using a comma b comma s comma co.
Yeah.
Now you declare the type input. Your size is vector a comma b. So since it is a 4-bit, so vector size must be 4.
Right. Yeah.
And if you perform the addition, you get some 4-bit and one carry out. That is a scaling.
Right.
So now you have to instantiate 4 times. 1, 2, 3, 4 times. What you have to instantiate means this module you have to instantiate here.
Yes. Yes.
So this module you instantiate here.
Okay.
This is highlighter. This is 10. So this FA, you use the name here, FA space, then the instantiation name, FA1 I'm giving.
Yeah. Okay.
Then what is that you want to bind with A? What is that you want to bind with B? What is that you want to bind with C in? What is that you want to bind with S? What is that you want to bind with CO? That order you have to follow here.
Okay. Here, same. Yeah.
So obviously, I want to bind with the first full adder instantiation. If you look at the diagram here,
Yeah.
what I am binding here, A of 0 and B of 0 with the first.
Right. Yeah. True.
So that's what you do here. You bind here A of 0, then B of 0.
Right.
Then what you are doing, the C in is tied to 0.
Right. Yes.
So you can put directly here there are multiple ways to actually do. One way is one take B0 directly you put here.
Okay. Okay.
So actually it means what is when you are instantiating FA here for the C in, this 0 will be tied.
Okay. Okay. Like that. Yeah.
Huh. The other way to do is you have to have here one wire, let's say wire. This is C in you are declaring, and you have to assign this wire. You have to assign this. You have to assign C in as 0.
Yeah.
You have declared wire keyword. Wire is a keyword, and the C in is a variable.
Right.
And you are assigning using the keyword assign, and you are assigning to this C in variable 0.
Right.
Now, instead of using this one tick B0 here, what you can use is C in.
Okay. Yeah.
So that is another way of doing.
Okay. Yeah.
Now you have done with A of 0, B of 0, and this C in, then comma. Then what is that? Your first instantiation of this is giving here. That is giving S0, no?
Yeah. Yeah.
And it is producing intermediate signal carry out.
Right.
So same thing you do it here. Same thing you do it here. So what you do is after this, you say S of 0, and
Okay.
then C 0.
Okay.
Let's say this is C0.
Yeah.
And then close this parenthesis. This parenthesis you started here. Na?
Right. Yeah.
That parenthesis you are closing here.
Got it.
And then semicolon.
Yeah. Yeah. Of course.
So this is first instantiation done.
Done. Yeah.
You have to
Same
do
way.
4 times like that. 1, 2,
Yeah.
3, 4.
Yeah.
So this time again what you do is you again do the same. Like you again FA. And this time the instantiation name is FA2.
Will
You
be
cannot
different.
have
Yeah.
the same name.
FSU. Yeah.
So then open the parenthesis. The second instance, what you are applying? A of 1,
A of one.
B of 1
Yeah.
you are
Yeah.
applying.
Right.
Then what is coming to the second instance?
Is
This
the
carry
CO.
out is coming, na?
Yeah. Yeah.
So that
CO
is
is coming.
C0.
Yeah.
This is C0, 0.
Right.
Then what the second instance is giving? S of 1 it is giving.
Yeah.
Then C1, intermediate signal C1.
Yeah.
Then terminate with a semicolon, comma.
Right.
Sorry,
Yeah.
close this parenthesis, then terminate with a semicolon.
Semicolon. Yeah.
So you are done with the second instance now.
Right.
So you have to do the third instance now. To do the third instance, again same FA, and then instance name. What is that you are passing to the third instance? A of 2 you are passing.
Yeah. Yeah.
B of 2 you are passing. Then what is
Right.
coming to the third instance? C1 is coming as the input.
Yeah.
C1. Then
Yeah.
what it is giving third instance? S of 2 it is giving.
Right.
And what it is giving the output is some variable.
Yeah.
So that's the variable we are calling C2.
Yeah.
Now you have done with third instance.
Yeah.
You require again one more instance FA.
Yeah.
That is fourth instance.
Right.
To the fourth instance, A of 3, B of 3,
Yeah.
and this C2.
Yeah.
And then this C2. And then it is going to give S of 3.
Right.
Then finally what comes is actual carry out. So that is CO.
Yeah. CO. Yeah.
And since you have done, it means the way that block diagram is that's how you have done the coding also.
Yeah. Yeah.
So it means what your connections are done in Verilog. Now you can close this with the end module. End module.
Right.
Over. You have done your description like
Yeah.
that.
Done. Can
Same.
you just go little bit up?
Hmm.
Mm. So, one question
Hmm.
in the first. Oh no, no. Okay, got it. No, nothing.
Okay. So
Yeah.
that's how you have done. Now what is that required to be done is test bench.
Test bench.
So in test bench, this is your FA 4-bit.
Right.
So now what is required to be given for this is we only have to give our A value, B value. That's it.
Right. Yeah.
So it will produce our sum and carry out.
Right.
This
Yeah.
A is a 4-bit, B is also 4-bit, S is a 4-bit.
Right. Hmm.
So how to give them means that is very obvious that you can multiple ways are there. For example, you are writing one initial statement and begin, and you are going with like applying A4 here, B6 here, giving some delay, then
Okay.
applying A14, B13, then giving
Okay.
some delay, like that one way.
Okay.
The other way is you
So
have
this is in the decimal way I'm putting. So if I put 4, automatically the system will convert it into four bits.
this I have covered in my first sessions. I
Yeah.
said
Yeah.
there are, by default, if you put this way, compiler is going to take them as a decimal only.
Yeah.
But this decimal number for that compiler, what it does is, on which operating system you have installed the Verilog compiler.
Yeah. You mentioned 32 or 64 bits based on that.
So if you
Right.
have installed Verilog compiler on 32 or 64, depending upon that, this
Yeah.
decimal number will be converted to these many bits. Just for
Okay.
6, what it does is
Yeah.
110, rest all it fill with the zeros.
0. Yeah.
But we don't want this kind of behavior means then what we have to do is we have to tell the compiler not to assign 32 or 64 bit, just assign this 6. 6 can be done with 3 bits. So 3 tick
Right.
B 110.
Right.
So
Yeah.
but since our B is a 4-bit, what we do is 4 tick B 0110,
Yeah.
just
Yeah.
because our B is 4-bit.
Right.
So in that case, compiler will not be taking this way, approach. It will stick to this one.
Yeah. Yeah.
So that's how you give input. But this is just I gave. I'm just telling how to write this Verilog
Test
code,
bench. Yeah.
Verilog test bench.
Test bench. Yes.
So this is one way of going. But the problem with this approach is how many you will write, because A required to be tested for 0 to 15.
Right.
B is required to be tested for 0 to 15.
Right.
For every case of 0, B required to be tested for all of this 0 to 15.
Yeah. Yeah.
For
True.
every one of this, B required to be tested for all of this again.
Yeah.
So like that, 15 into 15, you may go up to maybe 255.
Yeah.
But that way of writing is not recommended.
Right. Yeah.
So that's why what we do is we either can use like this, like initial, begin, for I equal to 0, I less than or equal to 15, I equal to I plus
Okay.
1. Here you put your begin, here you put begin,
Yeah.
and you assign here A. And then you have the loop here for j equal to 0,
Okay.
j less than or equal to 15, then j equal to j plus 1. Here you assign b value.
Yeah.
And then this begin end, and this
Yeah.
begin end. Now
Yeah.
what happens is compiler first this for loop, what happens is 0 will be assigned and it will go here.
Right.
Till this completes not this this complete loop, then it will be here.
Yeah.
So we have to apply the delay also here because otherwise we end up having the last value here. So
Yeah. Yeah.
here begin and end is required here.
Right.
Here begin and end also required because what happens is when it comes to this inner loop, J is 0 been applied. After 5 again it will go to the inner loop again.
Yes.
Then J will be incremented by 1 and this 1 will be applied here. Again after a delay, again inner loop will be executed.
Yeah.
So then once inner loop all 15 are done, then it will go to the outer loop.
Yeah. Yeah. Yeah.
But this is also not recommended. This is a one way, but this is also not recommended. Why? Because again, here also you, though like you managed all those 255, instead, going this way of writing like delay, then delay, all possible cases, you managed that laborious job with the help of these loops, but still this is
Yes.
also not recommended. What is recommended is to use this one, initial, begin, for I equal to 0, I less than or equal to 15, and then I equal to I plus 1, and then begin your A is assigned with dollar U random. U means this is unsigned random number, and then B with again dollar U random, and then end. So you are going to take some 15 random values.
Right.
So this is what recommended randomization.
Okay. Yeah.
So then if for these random values, if you could able to test your top level, this one, then it means
Yeah.
your logic is correct.
Okay. Yeah.
So that's how you handle this one.
Right. Got it.
Got it?
Yeah. Yeah.
So then what I recommend is just so if you have this FA in different folder, then that part I will cover and will stop. So let's say here is one folder, there is another folder, two.
Yeah. Yeah.
Inside this folder, you have fa.v file. Inside this fa4 bit.v file is here.
Right. Yeah.
So in that case, what you have to do is just before this module FA4 bit where you are writing the entire code, that above written code,
Yeah.
you have to put here backcode include and then the path here, path of this file.
Yeah.
So in double quotes you have to put.
Okay. Okay.
For example, let us say this one is /home /user in Linux it is like that /home
Yeah.
/user and there is like desktop on desktop designs inside designs that fa.v is there.
Yeah.
This entire thing inside the double quotes required to be kept.
Yeah. Yeah.
That is called the path.
Okay. Yeah.
So that way you handle if your some other designs are there in some other folder, but you want them to be used in the current module, then you use this compiler directive. This is called the compiler
Yeah.
directive. Earlier
Right.
we used another one compiler directive, if you are remembering, backport time scale.
Yeah. Yeah. Yeah.
So
Yeah.
this is another compiler directive. With this, what we have to
Okay.
understand is anything that is starting with a backport, that is the compiler directive.
Okay. Yeah.
Anything that is starting with a dollar, it can be a system task or it can be a system function.
Okay.
In our cases, so far we have used a dollar monitor we have used and a dollar
Yeah.
time we have used.
Right.
Dollar time is a system function for system function, it returns what is the job of this dollar time is it returns the simulation time.
Yeah. Yeah.
Whereas dollar monitor job is to put something onto the console.
Right.
So with that, we stop.
Okay.
And because you have